All right, let's get started. Hi, everyone. I'm Jinhua Zhao, Professor of Cities and Transportation at MIT. Welcome to the MIT Mobility Forum designed by the MIT Mobility Initiative. Today, I'm really excited to have Professor Chuchu joining us, presenting her research on learning with certificate functions for autonomous systems. So for as long as we've been designing control system, we always ask a question, how do we know the controller is safe, right? How do we really prove it rigorously, right? For simple system, like a linear one or low dimensional polynomial dynamics, we're able to just handcraft it. We can analyze it analytically and prove that it will be safe, right? But this annual approach quickly becomes almost impossible as the system dynamics and its controller architecture become more and more complex. And this is a particular case that in recent years, there are a variety of controller architecture using deep learning, either using learning from demonstration, like imitation learning, or solving nonlinear optimal control problem using the reinforcement learning, right? Although this learning-based controller has been rather powerful empirically, right? But they are prone to the very difficult to analyze failures and vulnerable to adversary examples. Yeah, and so complex, it's really hard to really understand what's going on inside. And this is very much the case in transportation, like our autonomous vehicles, autonomous drones. When they are using this complex deep learning-based controller, how do we know this is really safe? How do you even verify the safety of these complex learning-based controllers? Or even better, can we design the controllers with a built-in safety gardens and constraint in it, right? So today we're really fortunate to have Professor Van joining us to really give us his understanding and his cutting-edge research in this specific topic, right? Chuchu Fan is a professor in the Department of Aeroastro at MIT and also the Laboratory for Information and Decision System at MIT. Her research group named Realm used rigorous mathematics, including formal method, machine learning, and control theory for the design, analysis, and verification of the safe autonomous system. Chuchu is a recipient of the NSF Career Award, the AFOSR Young Investigator Program Award, and the 2020 ACM Doctoral Dissertation Award, right? Before I pass the forum to Chuchu, I do want to do a quick warm-up exercise. I would like to invite everyone in the audience to type in the chat your organization, your city, and time, so that we know who the audience are, and then Chuchu can potentially adapt to the present to the audience here. So I will type MIT, Cambridge, Massachusetts, and time is 12:05 p.m. Thank you. There are many universities. I also see Liberty Mutual, UCLA, World Bank. Cool. Yeah, SNCF, EPFL, Skyway. Great. Yeah, Airbus. Hopefully, this gives you some context about who the audience are, right? And lastly, I want to reinforce the norm of this forum, which is everyone contributes one idea. Right. For the audience, we'd like you to type in either one question to Professor Fan or a comments to the presentation in the chat. I really hope that everyone really participated by contributing such ideas. And in the third part of the presentation, John Moidati will curate those questions and comments and pass to Chuchu for her presentation. Right. So Chuchu, the forum is yours. Thank you.
Thank you. Okay, let me share my screen. All right. Can you see my screen now?
Yes, very well.
Great. Okay. Hi, everyone. It's my great pleasure to be here today to share some of our research on this thing called certificate functions. And Jinhua has given a very, very good motivation. I guess I'll be fast on my first few slides. I will. So as the title suggested, we are looking at this problem of how would we certify a for example, controller, when we want to learn this controller for autonomous systems and particular automotive systems for today's talk. And so I would like to start with what I mean by a certificate function. And their certificate function generally means something that is a mathematical proof that we can construct to show that the system will satisfy the desired properties when we design those. And the certificate functions we have been looking at are primarily around the control certificate functions. And they are originally motivated by control theory. And if you have ever taken any control theory class, you might be familiar with some of the names here. If not, that don't worry. These are some mathematical abstract of desired system properties. For example, when people design a controller and show that this controller is stable. So stable basically means there is a desired status of the system you want the system to stay on, even if there are perturbations that drag it away from this desired static state or fixed state, the system will automatically come back to it. And thinking about for example, I'm from aerospace department, so like a lot of my applications are in the aerospace industry, but the approach we've been developing can be applied to automotive systems a lot. Thinking about like flying a quadrotor that the wind could blow it away, you want it to get stabilized and come back. And in the middle is something called barrier function, is more related to safety aspects. Barrier function, as its name suggested, is sort of create a barrier from safe and unsafe. And if we can find a barrier function, it sort of certify that there's a region the system will stay on. For example, if we want the cars to stay within the lane, and if we manage to show that there is a barrier function that kind of align with the lane, then we can always show this lane keeping algorithm is working. And there's something else called contraction metric for certifying the system can track some arbitrary trajectories that could be used in the cases when there is a very slippery road and we want the car to be able to still track the desired reference path even if it's slippery. So these certificate functions, of course, is not created by us. They have existed for a very long time, and they have been very widely used in all different kinds of control systems to show that the system satisfies the desired property. Now, the question comes when we want to use learning approaches in automotive system. What's the difficulty of using these certificate functions to prove our system's property? So before I talk about a little bit about the technical aspect of how it works, I want to give an overview of what kind of a control certificate or neural control certificate can help with. Neural control certificate is this topic we've been studying of creating the certificate function itself as a neural network together with a neural network controller or controller policy that we learn. So we have, over the past few years, my group has established a series of studies on understanding how to certify learning-based control systems. And we call this neural control certificate. We have shown that the neural control certificate can help with, first of all, for single agent systems, it can certify learning-based control from high-dimensional input. By saying high-dimensional input, I mean those input directly from the sensor, like camera or LiDAR. And this type of controller can be made and certified to be robust. It can be used online, and it can be used in the adaptive way to handle uncertainties and failures. And I have listed a few references from my group discussing those aspects. Second, what we find very exciting about is the neural control certificate can really help in the large fleet of agents, like thinking about when we control thousands or 10,000 of agents. Like this background is actually the background of this slide is a simulation environment that we've been working on. It's like kind of like a future city we want to live in, where we have thousands of quadrotors flying around. Those are the tiny white dots. We have vehicles on the road, and we have all different types of vehicles that can serve our daily life. And we want to really control these agents with a very high level of guarantees that they will work correctly, they will not cause any dangers or harm our people. We have also studied neural certificates with respect to providing insights on how other uncontrolled road participants would react to our autonomous cars. And lastly, we have also been looking at how to combine the neural certificate with reinforcement learning to have something called the certificate carrying reinforcement learning. This is a special type of reinforcement learning that you can use any reinforcement learning approach that you like, but it will give you a neural certificate as a byproduct. So in today's talk, I probably won't have time to cover all. I will try to mention some of the application in the first 3 bullets. If you have interest, I'm always happy to point you to the references and let you know like what has happened in the other directions. Now, let me kind of narrow it down a little bit to talk about what it means by neural certificate for a very specific autonomous navigation problem. Thinking about solving a LiDAR-based navigation, a vehicle that has a LiDAR to read where the obstacles are. Now it's still moving. We want the vehicle to be able to avoid collision to anything that we classify an obstacle. These obstacles could be moving. And at the same time, we don't want to be overly conservative to be safe, meaning we still want the vehicle to be able to move on and reach its destination on time, wherever that destination is. But we want to have both what we call reach and avoid. And this is always certified in the safety aspect, and also the reach aspect is certified. Now, of course, there are a lot of people study this problem. Just from a control certificate point of view, how can we create a proof that this reach avoid using LiDAR is going to be successful and is going to be safe? Now, I'm going to have a few equations, and these 5 will be the only equations I show today. And I just want, with the goal of very roughly tell you how it works, why it can help with certifying this learning-based control. Now, regardless of how the dynamics of the car is created, what is a sensor, we're just thinking about this. There's some controller that reads a LiDAR input and will give the control command to the vehicle, basically give the steering wheel and the throttle of the vehicle. Now, if I want to create a control certificate, I'm going to desire for this function we call the control Lyapunov barrier function. And it more than that is a robust version. It's a single function that will map the environment information. This X you can consider to have everything, including whatever you can read as the vehicle itself, and also whatever the LiDAR input is giving it. Now, it's a function that will take this in and map to a scalar value. So the output is only a scalar. And we want this function to satisfy 5 conditions. And if you're familiar with control, you can quickly read that the first, second, and last condition is a Lyapunov function. Lyapunov function is a pseudo or generalized energy function people use to create to show that the system is going to be stabilized. Meaning in this case, it could be stay within the lane or get to its destination within a given amount of time. And the last 3 conditions here give us a barrier function. If we read the third and the fourth condition, it says, and in some cases, we want this when in some cases, when we can say the system is safe, we want the value of this function to be smaller than the threshold. And when it's unsafe, it's bigger than the threshold. So the third and fourth condition here basically give us like a classifier or a safety barrier, tell us when it is safe, when it is unsafe. And this can be defined as, collision avoidance is safe, and speed limit can be classified as safe, and whatever property that we want the system to satisfy. Now, if I can have this one function V for my controller, from a control engineer point of view, this is a perfect certificate to show now my controller will do whatever I want it to do, like safe, reach, avoid. Now, the theorem says if we can find such a function V, it can be used as a certificate for this particular control policy U that will take in whatever the sensor give it to it and produce the right control command. And the closed loop system is going to be robustly safe and stable in terms of goal reaching. This stable could be goal reaching, whatever that goal, like stay within the middle of the lane or some destination. However, it's not, of course, an easy problem to find such a V, especially when we are looking at this end-to-end learning approach, when the algorithm is directly taking the LiDAR input without doing like separate perception and modularization of all these different small pieces. And over the past 2-3 decades, there are a lot of different approaches, like sum of square. That's a big topic in the robotics group here at MIT, and simulation-guided approach to find this certificate function. But the computational complexity has always been a bottleneck so far. I'm not going to go into the detail of the different computational complexity, but usually these traditional approaches, first of all, it cannot handle very high dimensional systems. It can do like 6-5 dimensional, then go beyond that. It will be very difficult to find a certificate function using existing approaches. And also it's very hard for them to directly handle the sensor input. Now, the neural certificate idea here is pretty straightforward. The idea here is, now we know the conditions of the certificate function we wanted to satisfy. We don't know how it looks like. So what we're going to do is to represent it as a neural network. And of course, learning-based approach desire for a controller that is also a neural network. We're going to represent both as neural networks and blender the requirement of the certificate in the learning process. The way to do it is, so at the bottom here, I have listed a lost term. This lost term is precisely capturing the desired 5 conditions. It's actually more than 5 if we want to make it robust, but I just say 5 for now. I'm saying it's more than 5 because the last condition can be parameterized to have multiple to work for a very wide range of different environments. Anyway, so these conditions, this loss function at the last can be used as one lost term for the training of this neural certificate and the controller. Basically, if I use a diagram to represent this, as I said, both the certificate function and the controller are represented as neural networks. And we're going to collect samples to jointly find both using this loss term that I have listed below. And of course, we can also add other loss terms. We can also combine these 2 neural networks for the certificate function and the controller as one. There are a lot of flexibility here. And I will skip the details here, but the idea is this certificate, once we represent it as a neural network, we can blend the whole learning process with the constraint of satisfying the certificate instead of just empirically improve some performance and try to verify it. That would be a much harder problem. And if I want to quickly show you what a neural certificate looks like, what I'm showing at the bottom here is a observation-based control barrier function on the left, and also observation-based Lyapunov function on the right. But if we look at the barrier function, you can see that gray regions are some estimated obstacles. And the certificate function, if we visualize it and project it from the high dimension to this 2D space, we can see it actually align very well with what we desire for. We basically, in the middle, the barrier function want to create a nice barrier, which is the green, circles here, the curves here. They tell us what is safe and unsafe. It always drives the system to the safer and safer area. And another advantage of using the neural certificate is now, because we have very advanced architectures. For example, oops, sorry, this is somehow one second. Let me do this again. I don't know why my slide kind of got zoomed in a little bit. Oh, okay, now it's back. All right, sorry about that technical glitch. And I was saying another advantage of neural certificate is that we have the advanced machine learning tools like embedding to help embed the changing LiDAR measurement into something that we can handle using control theory. This is not possible if we go with the traditional approaches. And I also mentioned another benefit of using neural certificate control is this can now become really online. So using neural certificate control, when we control the system, at each time we are just evaluating a neural network, or we are solving a much smaller optimization problem. This really can achieve much higher frequency of a control, and the computation can be finish within a given amount of time, versus the traditional MPC, for example, model predictive control. It has a much larger computational time because it's solving an online optimization problem. The biggest problem with MPC is that it cannot be used online. So if the robust MPC will work fine at 10 hertz, but the computation cannot happen within that 100 millisecond. If we really want to use it, use it in real time, like for this particular tracking case, you can see when this road is slippery and the car can have like can slip around, and then it's not doing a very well job if we want to use the real-time control. And I want to quickly mention that the biggest advantage I see about neural certificate is really this generalizability, particularly for a multi-agent system. So traditional ways of handling multi-agent system, like you have to go either centralized or decentralized, or a blender of centralized and decentralized way. And we do see that the trade-off is centralized way is easier to understand and to certify, and decentralized way is much more scalable. The benefit of neural certificate is now we can have a certified way to do fully decentralized control. And the setup is the following here. I'm showing a very simple scenario where it's not exactly automotive systems. We don't have land. It's kind of more of like a free space when the cars can move around. Now the car, we have a few agents here, and they can build a communication channel when they are close. So you can see there is like a thicker line established when these agents are close, and they also have LiDAR. So these thin lines are the LiDAR rays that the vehicle have. The vehicle have no knowledge about where others are and where the obstacles are, but they are asked to go to their destination. To handle such multi-agent system and to generalize to different settings, we really have to go after a fully decentralized approach to be able to handle, say, changing number of agents, changing environments, and really go to a very large scale. And in the next slide, I will show you why neural certificate can tackle this problem and make it even certified. And for a multi-agent system, it's naturally a graph. And we can actually build a graph control barrier function to guarantee the safety. I'm going to be faster here. For a graph here, the setting is slightly different. The graph we are building have two types of nodes. The node can be an agent, or it can be a hitting point of the LiDAR array in the observation space. So thinking about the cloud, the point in the point cloud in the LiDAR space. So each of those point would be an end node. Each of the agent is also an end node. If you don't treat them as obstacle, of course you can also treat them as obstacles. And the edges are defined when two node are close enough. Basically, within a sensing range, you can either talk to the other neighboring agent, or you can detect there is an obstacle here. Now, a graph neural control barrier function, I'm not going to read through this, but this is exactly the same as slide number 3 when I give the general definition. It's almost the same, but it's now defined over a graph. We have the edge feature, we have the node feature to denote what kind of edge, what kind of communication we are desired. So we can establish theorem that the existence of a graph control barrier function will guarantee the safety of multi-agent systems for non-colliding initial conditions. If we are going to, the way to learn it is more or less the same as what we just said. We will blend the conditions of this graph control barrier function into the learning process. And what we can get here, so it's the simple case of 4 agents. The orange dots are agents or a car, and the black dots are the endpoints of the LiDAR array. Now, when we trained in the training process, we don't even have to explicitly establish what is the obstacle. We just randomly sample the points in the point cloud. And those points could represent obstacle. It could be another random thing. But we ended up having, for example, this is a case of what is learned as a barrier function for the agent here in the middle. You can see that it nicely captured the neighbors, and the closer the neighbor are, there's a higher weight of paying attention to this neighbor or to this endpoint of the obstacle. And we can also establish very clear boundaries of safety versus unsafe. And basically, if we can learn such a graph barrier function, we can certify the entire safety of the multi-agent system. Now, this can generalize very well. We trained on a small number of agents, like 16 Dubin's cars. The resulting controller can be deployed on an arbitrary large number of agents of the same dynamics. If the dynamic change, we will have to find another, to basically find another controller for that different dynamics. But vehicles with the same dynamics can share the same controller and the same piece of the graph control barrier function. This is fully decentralized because we learn it as a graph neural network. And the graph neural network has this advantage of having a fully decentralized deployment. Now, as I said, we trained with 16 cars. This controller has been deployed on thousands of vehicles, and there won't be any collision that we can even find. And another interesting observation we have is we can handle changing environment. For example, we train the vehicle on the left. I know it's very difficult to read because the vehicles are very, very small. It's a very sparse environment that we use for training, but we just dump more and more such vehicles into the environment. Of course, at some point, it will be so crowded that the vehicle cannot move around. But this type of safe controller can generalize very well to much more dense environment. If we read the more quantitative result, we have tested across different dynamics along and also different kind of settings when we kind of increase the density or keep the density, or kind of the bottom one here is basically the same setting. We will keep the density the same and also ask each vehicle to travel almost the same length as if they were trained. You can see that even for thousands of vehicles, the red curve is a performance of this approach. It will stay almost like 100% success. Success means all vehicles reach their destination on time without being involved in any collision. So the safety rate can almost keep the same and generalize to as many as we want. When we put them in a more challenging environment, like we increase the density or keep the density but ask the vehicles to travel much longer, the performance is kept pretty good until the environment is too challenging that cannot even be handled. We can, as I said, the vehicles are trained without, let me see if I can play this, without an explicit model of the obstacles. Now, the freedom it brought us is we can put as many obstacles as we want. They could have different sizes, different moving speed, moving velocity, and we can put a lot more agents into the environment. You can see that the control policy really handled this generalized environment pretty well. If we compare this with, for example, multi-agent PPO, a reinforcement learning approach, you can see how overwhelmingly our approach good. With the increasing number of obstacles here, our success rate is kept almost perfect, while reinforcement learning is very struggled with this type of settings when the vehicle never saw this type of obstacles before. As I said, I work in the aerospace department, so a lot of our applications were put into the aerospace type of environment. Here, I'm showing some demonstration of the different types of robots or different type of vehicles moving in the simulation environment that I introduced at the beginning. And as the approach is general. Of course, for automotive systems, we will have to look at different aspects of safety, but because this is a data-driven approach, all these different considerations of safety can be blended into this learning process, and we can have a pretty unique way of certifying the safety of the controllers. And before I land the talk, I want to briefly talk this pretty interesting set project we've been doing of understanding what other use of neural certificate we can have. It turns out that we find neural certificate itself can be used to capture the human intentions. And this intention can be learned from the real world traffic data. And now if we capture or abstract the human intention as neural certificate, like the intention of avoiding collisions or how you want to avoid collisions, or the intention of following traffic rules or how much you want to follow the traffic rules. It can be abstracted as the neural certificate, and we can insert this kind of back into the learned human behavior models to understand how other road participants will react to our autonomous car. It's another thing that I feel pretty interesting here. For example, thinking about this particular environment when a bicyclist wants to travel through this small intersection before a roundabout, actually in terms of safety, the setting is almost the same as what we just saw before. Each person will have a observation range. It will look at what's happening in the neighborhood, treating them as some sort of moving obstacles, and decide how much it wants to avoid the collisions with the other neighboring road participants. So once we do that, it turns out this type of human behavior model can actually generalize to unsaid scenario much better than if we just do imitation learning. In here, what we did was from a traffic data set of pedestrians moving in the intersection. And now the pedestrians never saw a car moving from the right before, because it's a one-way road. The car can only move from left to right, but we cannot eliminate the possibility that the car could go the opposite. Anyway, in this data set, there was never a car moving from the right. If we look at the original trajectory, the pedestrians are just moving one direction, and there's no way for the car to bypass this scenario. And if we use imitation learning, because the model never saw a car from that direction before, it kind of going all the places, and wow, that we couldn't even explain why it's doing it. Now, if we blend the certificate that capture the collision avoidance intention of these people, you can see now on the right-hand side, they really have a much more reasonable way of avoid a vehicle if it's moving slowly. And in this way, we feel it can help with understanding how we can better build a reactive road participant model for different traffic scenarios. And again, this is purely data-driven, so the same approach can be used for different type of road participants, and kind of instead of use imitation learning to learn their control or their policies, we actually we learn the intention and abstract those as different types of neural certificates. We can even blend traffic rules into this kind of idea. Here, each of the blue car, when they were trained, not in this scenario, they were trained separately. When we train their controller, we can actually insert some traffic rules like safety, or basically keep some safe distance to the front vehicle, how they react at the stop sign, how they react to a traffic light, all these rules as different types of neural certificate for each of this learned model. When we put all these vehicles to a much more complex scenario, we see that these vehicles, the blue ones we have, they always follow the rules that we originally put in, versus on the right-hand side, you can see their red cars, they are not really following the rules that we have defined. And we can say that in these scenarios, if there's a collision, the cause is always the other vehicles, not us. So let me just summarize what I've talked about the neural certificate and how they're going to be used in urban mobility systems. We believe that neural certificate can provide a quantifiable way to certify learning-based control, especially those control from sensor input, directly read the sensor input and decide the control actions. These controllers from neural certificate can be designed to be robust, to be used online, and adaptive. And I didn't get a chance to go into the details of this specific aspect, but we have different works discussing the special properties here. What we really like about neural certificate is that it can provide a fully decentralized, scalable, and generalizable way to deploy collision avoidance control for vehicles. And the neural certificates can capture some human intent when we want to build models for the other road participant, not the ego vehicles. There are many, many applications using neural certificates, and I feel bad to say, but most of our applications were actually in the aerospace. We have used neural certificate for flying different types of quadrotors or fixed wing, and use those on the satellite systems. I guess one aspect is because we work in the aerospace department, and the other aspect is for aerospace applications, it's actually easier to deal with, in the sense it doesn't really interact with a lot of people around. But for automotive systems, we acknowledge that there are many aspects that we are not really considering in this framework. And one last thing I want to mention before I close the talk is some of you may already kind of have this question, the neural certificate is learned. How can I even say it's a certificate? I want to emphasize that what I have introduced is approach to find a candidate certificate function. And still we need formal verification tools to verify these certificate functions to really say this works for every case, not just the samples that we collected in the training set. But we still think this is a much better approach because the verification problem for a certificate is much easier than a verification of a dynamics. For dynamics, it's a high dimensional, and we have to see the involvement over time. So you have to unroll the behavior. But the neural certificate is a static function, and the output is scalar. So compared to verifying a high-dimensional changing environments dynamic system versus verifying a function that only output a scalar value, it's a much easier verification problem. We have other work discussing how to verify certificate functions once they are learned. I won't have time to cover those, but I'm happy to discuss. And on the left here, I have listed a couple of papers that I draw some of the pictures and videos from. At the bottom, there is a QR code that link to our group and also our GitHub. Whatever I have talked about, including like the simulation, the demos, the code in the GitHub, feel free to check those out. Okay,
perfect.
so
Thank you so much, Chuchu. This is really fascinating. Here, I have a couple of questions to start, and also encourage the audience to please do add your question to it, particularly the control theory expert to add comments and a question on this, right? So Chuchu, maybe I'll start with a simple one. In one slide, you compared the performance between cars, roving car, and the drones. Can you go to that slide? The where density increase, what the performance changes. Yeah, exactly. Yeah. Yeah, exactly. Yeah. So on that, I can understand that when you keep distance, then the GCBF almost reached 100% performance, right? But when the travel gets longer or density gets longer, some performance can start to decline, even though it's always better than the other approach.
Yeah, it is.
Notice
Yeah.
that for the drone, it almost keeps 100% all the time. While in contrast, for cars, it starts to decline there, right? Why this case?
So the easiest answer for this is drone has a much easier to do collision avoidance because they have a 3D environment to avoid collisions versus for cars. The at some point, it's just a 2D space when it's like if we increase density, basically it's just like this much of a space. You dump more and more agents into it. At some point, they just do not have a way to avoid each other. What will happen? I didn't really show the breakdown of the performance. The safety is still pretty high, but what will happen is a lot of them will get locally stuck and they will not reach their destination. The safety is still guaranteed, but the reaching part is kind of going to go down a lot. Then that causes the success rate to go down. So that's basically the first reason. The second reason is drone is a fully actuated system. So you have if we design it well, it can almost work as like an integrator to move in different spaces. But cars, they are under actuated system, right? Even if we know if we turn by this hard, we can avoid the collision or we could go to the destination. But the car will have the control limit, as well as we can only, for example, control the acceleration. We cannot directly control the position of the car. So this under actuated system is much more difficult to control. That will cause the performance that for drone is actually a much easier problem to solve than for the 2D vehicles. Great,
thank you. First of all, we should attempt you more to get into the surface transportation field, or to invite more to do the research on this, right? So to further complicate the thing in the surface transportation versus the drone is that we have all sort of agent in the surface transportation system, right? They are both multi-agent, but they are also multimodal in the sense of there's cars, there's bicycles, trains, and also when we talk specifically about the autonomous vehicle, that there will be a long period of time where there will be mixing between the autonomous vehicle versus human-driven vehicles on this, right? What do you see this type of complexity that your method that can gradually tackle some of this?
Yeah, so that's definitely a very big challenge. And as I said, like that's why it's actually easier to deploy these things for aerospace application than autonomous vehicles. I think a lot of the directions we are working on, or the advantage of this type of neural certificate, can actually be used to tackle some of the challenges here. For example, we have different dynamics, but when they have the same dynamics, they can really share the similar copy of the certificate function and also the controller. So for this type, for the approach, we can actually easily extend this to heterogeneous agent systems but the computation will be slightly more difficult because for each type of agent, we'll have to separately, so their controller and the certificate will be different from the agents with different dynamics. And also, I think the decentralized aspect, like here, we are not asking every agent to know what's happening everywhere else. It only keeps a local communication and local observation. So when there's a close by agent, if they want to provide some information, they can establish a communication channel. If they're far away, we don't really require them to talk to each other. The agent will also keep like a LiDAR to just see what's happening around. Our approach, we try to build our approach to be less dependent on, for example, how large or how the obstacles are models. So we kind of try to eliminate the explicit model of the obstacles or the explicit model of what concrete type of communications we want to establish. So we're trying to build a general framework that can handle each specific case. When we have those specific cases, can be kind of easily fine-tuned to handle those cases. It's a longer term goal, but I think a lot of the design here is trying to tackle the complexity brought by the heterogeneous agent and also the kind of different considerations we have to have for different type of agent on the ground vehicle side.
Great, thanks. Yeah, the next question may be a little bit abstract in nature. So at the beginning, we mentioned that previously we have a control system, and then we have a handcrafted certified that it's very hard to identify. But once identified, you can verify it straightforward, right? But now we use the neural network as the certifier, right? So the neural network learn from those data, discover this certifier to the point where using the neural network as a theory discovering tool or theory building tool on this, right? So once you have the neural network, can you go inside it and understand what it's doing and then inspire a handcrafted certifier for that? Does that make sense?
Yeah, that makes sense. From a formal verification point of view, I spent my entire PhD developing formal verification tools. From a formal method point of view, a neural network is a white box because you actually exactly know once you have it. If it's open source, let's say, then you know exactly what he's doing. It's a composition of some sort of functions that he's doing. So we can develop verification approach. There are a lot of people working on verification of neural networks. So I would say once we verify these neural certificates, we can directly use them because we fully understand what this neural network as a certificate function is trying to do. And there are a lot of work from other groups. Some of the things we're also trying to do is to use this already certified certificate, neural certificate, as some sort of a runtime on monitor or a safety filter running on top of the system to kind of monitor when things goes wrong. And if anything could go wrong, it will do like a minimum perturbation to the system to drag it back. So that I believe in the future, we can directly use these certificate functions, even if they're represented as neural networks, but of course, fully verified as like an umbrella certificate or umbrella monitor to guarantee the safety of the system.
Yeah, probably the last question from me, and then give it to John for the audience question. Please, again, I encourage people to put your comments and question in the chat, right? So here, Chuchu, at the beginning, you mentioned that here you are putting both the controller and the certifier as neural network and learn them simultaneously, right?
Yeah.
Another pathway is if you have a certifier there and you can embed the certifier as a constraint for you to discover the controller. Can you give us a more detail on the second approach here?
Yeah. So that's a very good point. And actually, sorry, I didn't mention. So the very initial way of using neural certificates is what I just described. But actually, the certificate itself, they are called control barrier function, control layout functions. They are exactly used as what you have just described. In a lot of the cases in our example, we are not like there are comparisons. We can directly use the control policies, but those tend to work well for the environments that are closer to the training environment. For if we want to use those on some other environment that's kind of very different from the training environment, the way to use it is to use the certificate function to I wouldn't say to use certificate function to find a completely new controller, but using your certificate function to as the way I just described as a monitor and a filter on top of any controller. It could be the controller we learned here, or could be another controller other people want to use, and just use that to guarantee the safety of any type of controller, doing like a sort of use it as a filter or as a monitor to do a perturbation if anything goes wrong. So it's indeed used in the second way we just described, and it's a much more common use than directly use a learned controller.
Right. Great. Yeah. Thank you. So now let me invite John for the audience questions. Yeah, please, John.
Super. Thank you so much, Chuchu. We actually had slightly fewer questions than normal because I think the nature of this presentation was, very math-based and technical and so forth. But nonetheless, the questions, we had some very, very good questions. First, just to kick off, a simple question from Xiaojing, which is, are the simulators that you used open source?
Yeah, so the simulators we use, let me explain this a little bit more. The simulators you have saying, I just showed, I wouldn't even call them simulators. They are more visualizers. They're game engines. So the physics are separate. We separate the physics from the visualizer. Now, I know a lot of you use like ROS, and then the simulator is already, the physics already blended in the simulator. So what we do is we keep a separate physics, and that we can change the physics as if we want. And the whatever you see in the video is just the visualization in the game engine. So these two are separated, but both are open sourced. Everything is open sourced. I hope that answered the question. And the reason I would like to keep it this way is because, first of all, our approach is developed for general purpose. We don't want to tie it to any particular dynamical system or any particular physics. We want to have the freedom to do plug in of the physics. And other part is, if we do this way, the training happened completely without the visualizer. The visualizer is just the end step of showing what's happening. So in this way, it's much faster to do the training and the learning process than having a gazebo, for example, as a simulator. Then you have to constantly talk to a gazebo, and that will take much longer time.
Super, that's clear. We had a great question from Kenneth Capron, which is, have you ever considered existing systems as used in the automation industry? They already have all the physical components and software for collision avoidance and communication between devices. Rockwell is a good example, and they offer open source software. So any relationship with automation?
Yeah, I would like to explore. As I said, I didn't show any of the applications. I would say 95% of application we have currently are on the flying vehicles, not the ground vehicles. And actually, the way we do it is considering existing hardware and architecture. So we're doing, for example, using whatever the way I described to guarantee the safety of a fixed wing airplane. And this fixed wing airplane already come with all its design and all its communication protocol and also the hardware. Now what we do is to find a neural certificate that can act as, first of all, guarantee the safety, and also act as a filter to on top of their original control design to make sure like we just monitor whether it's doing the right thing. If not, we will correct it online to make it do the right thing. But I would like to explore more opportunities in the automotive industry. I tend to have more engagement with the automotive industry when I was a PhD student, but that was before I joined MIT, before I started to do this machine learning in the system. When I was a student, I developed tools to verify a Toyota powertrain system and their transmission system. Those are the more like old-fashioned verification of systems that doesn't really involve any machine learning component.
Fantastic. Hejon Huang had a question. Like bipedal robot foot movements, dynamics can switch periodically.
Mm-hmm.
Can the neural certificate you mentioned function online and handle these system transitions?
Yeah, that's also a very good point. We have some work of doing neural certificate for what we call hybrid system, and the way we call it hybrid system is like hybrid of continuous and discrete. So there will be continuous dynamics, but the dynamics will transit in between different continuous mode. I wouldn't say there's like, we cannot use the current neural certificate directly on those systems because this certificate kind of tied to each particular continuous dynamics. But we have work published last year about how we create certificate for hybrid systems that can not only guarantee the performance of each mode, but also guarantee the transition will be okay. Like when you transit, you also land into the certified region of the next mode. I'd be happy to share some references if you send me an email.
Super. Actually, if I may, I'd like to just inject a question of my own that builds a little bit on Jinhua's contrasting of the automotive or surface world with aviation. And that is, I mean, you have presented us with this amazing control theory and computational theory behind what do you do with a LiDAR signal. Now, my question would be, why do you think we haven't seen as much LiDAR being introduced into the world of commercial aviation? Do you see that coming in the future? We know that 2 years ago, there was an agreement between Airbus and Luminar, a LiDAR company, to explore implementation of LiDAR into commercial aviation systems. And we've also had a number of very dicey near misses here in the United States in our aviation system. Do you see LiDAR being introduced more into the world of commercial aviation?
I have to admit that I wouldn't be the expert to answer this question. I have heard people discussing why LiDAR is not a good idea to introduce to the aviation system, and there are a lot of different aspects of a consideration, mostly considering the performance of LiDAR in the more extreme environments that the aviation system will be. Like LiDAR will perform the best when it's outside, then you have to do all the aerodynamics analysis and also the extreme temperature, extreme wind, and that will, I guess that will be, you will have to need different design of the LiDAR system, and also how much we can trust the LiDAR input in those extreme environments in the aviation system. I heard people commenting that it will be a longer way before LiDAR will be used in commercialized systems, but I don't see it's necessarily like a dead end there. I think that's more like the sensor hardware people will probably have to put more effort. And another comment I want to make is, to us, what we care about is some sort of sensor measurement that can give us a distance information. It doesn't have to necessarily be a LiDAR. In aviation, radar is used more. And now people are also discussing camera and images. So I would like to see approaches that kind of less dependent on the particular type of sensor, but just like what kind of information we can get and what kind of guarantees we can build on top of that information is something I'd be interested to know. Yeah, sorry, I don't have a good answer here. I have less knowledge about the hardware design in aviation system with a consideration. Just overheard some conversations about that, like, oh, it's hard to imagine like the very fast fixed wing airplane will have the LiDAR somewhere outside.
Fair enough. Thank you. Thank you. So I think we have time for one more of the more technically oriented questions. So this one is from Ricardo Fiorista, and he writes, for GCBF, is there an attention mechanism in the NN setup? So is GCBF a combination of RL and certificate barrier functions, or is it absolutely sufficient for the agent because Chuchu compared their GCBF approach with RL? Honestly, I don't even understand the question. So I would ask if Ricardo's here, he can chime in. I'm hoping you do understand the question.
I think so. So GCBF there, so the way I introduced the example I showed was not in reinforcement learning. It's more of a naive approach of directly learning the controller and the GCBF both as graph neural networks. They tend to perform pretty well, but then the limitation here is we do have to know the dynamics of the system. In the setting when we do not have information of dynamics in the model free setting, we have to do RL. And we have a very timely question. We have very recent work discussing how to do reinforcement learning with GCBF learn as a graph neural network. So the short answer is yes, we can do it. I didn't show it, but that's possible.
Yeah, before I conclude, I will ask one last question. Toward the end of your presentation, you mentioned that this neural certificate happen to be very similar to the human intention, right? So you can use that as a way to understand human intention. That seems a very intriguing pathway. Can you elaborate a little bit more?
Yeah, so the idea here, I was trying to, like, when I firstly thought about this problem, I was from a testing point of view, we do not ground for autonomous vehicles, for example. We don't just test the ego vehicle by itself. We actually want to test when it will go wrong, and that will involve how the other people will react to us. Now, I have seen a lot of work of understanding how the other people will react to the autonomous vehicle. So they don't just move as they're, as if like a zombie. I think a lot of the current simulator just give you a zombie there. You give a path, it will follow the path. You hit on it, they won't really try to avoid that collision. So I was thinking, if we look at all these other road participants that we want to put in the testing environment of our ego vehicle, what's a reasonable way to model their intention? So for example, if I'm a pedestrian moving there, the way I want to avoid collision with whatever other like people or car around me works very similar to the mechanics of a barrier function. So I have like a mental barrier, what I think is a safe distance to me. And I will observe if that distance is getting smaller, I would tend to make that distance larger. And maybe there's a comfortable distance I will be happy to keep. In some extreme cases, when I cannot just be very far away to everyone because I need to go to my destination, there is some tolerance I can have to be close, but I still want to keep a very close barrier. Similarly, for the traffic rule, there are some like quantitative measurement of how much I want to follow the rule depending on the current traffic situation. So that's kind of the initial motivation. And then we're trying to see from the very large real world traffic data, can we learn the parameter as if like we try to use the certificate to model the intention, but there is some parameter to describe how much you want to follow it and do a regression of those parameters. It tend to work pretty well. And then we insert, now we know how to, when we learn a system, how we insert a certificate function. Now the idea here is when we do imitation learning, we don't just copy what we have said, we learn their intention. And when we copy their action, we also insert the certificate as their intention. Now they react as if they want to follow their intention, not just copy what they have said in the traffic data set. I think that's the motivation there. I think there will be a lot of interesting work to explore here.
Right.
But my bigger goal is to be able to create some road participant models that are reactive and making sense, and we can explain why they choose to do that as a much better testing tool for the autonomous vehicles.
Oh, that's fantastic. Chuchu, when you make more progress on that angle, we'd like to invite you again to share with the audience of what you learned from that. Yeah. So everybody, please join me thank Professor Chuchu for the presentation.